final assumption is that we can two possibilities, G equal to minus G prime or G equal to G prime. So then we examine these two cases to try to rule out one case from the experimental data. So in this case, we find that M1 and M2 almost degenerate, so it's consistent with the experimental data. And for the other case, we find that M1 and M2, they are not degenerate, and actually M3 in between. So this is inconsistent with the current experiment. So we conclude that we should choose G minus G prime. And it turns out that such kind of mass matrix have D4 symmetry. But of course, it's more restricted by just considering D4 symmetry, because D4 symmetry only have two-dimensional representation and one-dimensional representation. So the two degenerate mass belong to some two-dimensional representation, and this separate one belong to a separate one-dimensional representation.
So how do you see which solution is consistent with data?
I will show you the experiment data. So yeah, experiment data basically like this. So this M1, M2 very close. So M3 either much bigger or much smaller. So only have these two possibilities. But yeah, in the if G equal to G prime, we see actually M3 kind of in between, so it's inconsistent. Yeah, so here I just mentioned that this mass matrix, if we take G prime equal minus G, it's more kind of restricted than just by considering D4 symmetry. Because if we only considering D4 symmetry, basically there's no constraint for the ratio of the M1 and the M3, because they belong to different two-dimensional representation and one-dimensional representation. The ratio can be anything. By D4 symmetry, we can only kind of enforce this kind of mixing pattern, not the mass ratio. So that's one part. Okay, so now we compare to the experiment, so we find that actually we propose that it's an inverted pattern, and there's a special ratio between M1 and M3. It's 3 over square root of 5. So that's a very unique prediction. And also you can easily compute this neutrino beta decay mass, effective mass, which is very small due to this there's an interesting cancellation mechanism. Basically, the U1 square and U2 square, they have different signs. So you will see that basically they cancel and make this extremely small. And the overall scale of this neutrino mass is around like 75 MeV. So maybe it can be examined by future experiments. And we also have a unique prediction for the CTP violation angle. But I don't have time to explain, but just some phenomenological kind of calculation by adding some complex phase in the mass matrix, and you try to make a best fit to the current observation, and it shows that actually it enforces this CTP violation angle to be plus minus level 2. And such kind of maximal pattern also supported by recent experiments from the T2K results. They have a best fit, basically, it's minus pi over 2. And also, this kind of pattern, actually, if we add some phenomenological complex phase to fit the pattern, we find that there's very interesting Z2 anti-neutral symmetry. Namely, usually we think about muon and tau exchange symmetry because the theta 2,3 is maximum. But it turns out such kind of symmetry will lead to 0 theta 1,3. But we can enforce muon and neutrino, muon and tau exchange symmetry combined with a complex conjugate. That's the meaning of anti-unitary symmetry. Just like when we exchange muon and tau, we also reverse the time. So if we impose such a very strange combined symmetry, we can enforce this CTP violation angle to be maximum, plus or minus level 2. And also we can further generalize this scheme into quark sectors just by adding some phenomenological parameter, lambda and lambda prime, because in quark sector we have huge mass hierarchy because the standard model interactions. So we don't know how this parameterize, how this parameter comes from. But if we phenomenologically put it there and just compute this neutrino mass ratio from there as a function of lambda and lambda prime, so we try to make a best fit for the current data. this is a measurement, 18 and 47. 47 have some ambiguity because they have a range. We put the upper bound here. And also for the down clock, we also choose this ratio. But the relevant part is the upper clock, not the down clock. And in such a kind of setup, we see that magically this CPM matrix fit the experimental CPM matrix measurement up to 40 digits. So it's kind of magic showing there's intrinsic correlation between mixing angle and mass ratios. But of course, here to fit the CP validation angle, we need an additional fine-tuning kind of phase vector in the mass matrix to fit this complex phase in the CPM matrix. Okay, so let me just conclude. So the basic idea is that I propose that 4-component Majorana fermion can be further decomposed into 4 topological Majorana modes at cutoff scale. So that's the basic physical picture. And based on such kind of picture, we define some new types of CPT symmetries for the Majorana field, which is compatible with the Lorentz invariance. And in such a way, there's a natural way to explain the mixing pattern and the origin of these generations. And phenomenologically, we find this generation also successful for quark cells. But we don't have a microscopic explanation so far. So for future for future kind of direction, I think in this scheme there's a natural way to explain the 1, 2, 3 gauge field. This might be also very promising progress along this direction. And also we found some new types of supersymmetry that actually that might be, we don't need even add additional superpartner. We can just pair up this bosonic field and the fermionic field within standard model to make a superpartner. So this kind of we call it twisted supersymmetry. Basically, yeah, the basic idea is that the supercharger may also carry a certain gauge charge. And okay, thanks for your attention.
Questions?
I'm not sure if I followed it correctly. So you have 3 generations because there are 3 ways of.
Yeah, pair up the 0 mode.
So you start with the same 4 quantities to construct 3.
Yeah. So at a cutoff scale, you start from the same 4. Yeah. But at the low energy, you will have 3 because at a low energy they transform differently on the CPT representation. So it's like 3 different fields.
But the physical degrees of freedom are the same.
Yeah. So the point is that at a cutoff scale, there are only 1 generation, and we see 3 generations because yeah, you can also think of this problem in some different way. You can think about the flavor symmetry is like a gauge symmetry. So if it's a gauge symmetry, basically means at a cutoff scale, it's kind of they share the same degree of freedom. But at the low energy, you can have a deconfinement phase, and they can become 3 different generations. So this is very normal and usually happen in condensed matter system. Kind of in a fundamental lattice scale, you only have 1 degree freedom. But at the low energy, you can have kind of relativistic dispersions at different momentum points. So you can have more branches.
I guess in your lattice regulation of the 4 fermion modes, I guess you construct it on the qubit lattice.
Yeah.
Okay. So I'm just wondering because like in usual type 2 superconductor, the topological excitation of the vortex when they form lattices, it's not a square lattice. It's a triangle lattice. So what's the basic?
Oh yeah. So that's just a simple example. I'm not saying.
But in order to get a correct pairing scheme, you need a qubit lattice, right?
I don't think so because the pairing symmetry has nothing to do with the vortex lattice. The pairing symmetry just.
And the pairing between those 4 Majorana modes.
The pairing between the 4 Majorana modes basically just need some special hopping pattern. You don't need necessarily to put on square. You can put it on any lattice. And yeah, maybe I'm thinking maybe more a better way. Maybe some dynamic lattice. You can think about it, it's not a fixed background. So I think no problem. You can put on triangle lattice. Just you design this hopping in some proper way, you can still find a relativistic dispersion. But maybe a better regulation try not to break order symmetry at a cutoff scale. You need some string theory regulation or some TPFT regulation. So yeah, that part I don't know. So here it's still conjecture that such kind of regulation exists at a cutoff scale. You can really cut off. You can really decompose this four Majorana mode into some local version, and then they interaction in a certain way, such that at low energy you can produce this standard model. But this detail I don't know. It's very hard to check.
Yes.
How are you going to get a non-zero theta once reality theory? It seems that you need to break the D4 symmetry.
Yeah. That's true. So yeah, that could be a quantum effect. Yeah, at the present, in this semi-classical approach, I can only produce this so-called leading order pattern. So if you phenomenologically add some complex phase, you can get non-zero theta 1, 3.
But the whole point is that I start from the fundamental theory, right? I get, well, at least I get a non-zero theta 1, 3.
Yeah, if you have a quantum correction, yeah, it's possible you can get a non-zero 1, 3. But classically, I'm just claiming this classical calculation will give 0, 0, 1, 0.
If the G2 gets filled enough to bind this Majorana into the 3 generation of neutrino and low energy, can this be checked from your model?
Sorry.
So, I mean, you have 3 way of pairing from the 3 generation. It's
Right.
kinematic, just kinematic point of view, right? Dynamically, how can you make sure that from the bound state in this way in the
I
low
think so,
energy?
because if you think about the Z2 gauge theory, it's confined in the low energy. So so at the low energy, I think this Majorana mode is kind of carry some certain Z2 gauge charge. So they energetically, I think there's no problem to argue the confinement at low energy.
More questions? Okay, then thank you, Zheng-Cheng, for this very nice talk.
Prediction 就是那个leading order 的这个 mixed matrix 那个last ratio。还是假设 G 跟 G， 对，主要假设它们一样，比较弱一下。
你有 G 跟 G 号，你13号，其实一个推手要对 G 跟 G 号，但是马上你这个在系统
yeah， 就是 in principle， 你如果允许 G 跟 G prime 如果不一样的话，那么就different。
那也就跟他说，其实
但是你现在是fix G minus G prime， roughly 它有这个 pattern， 一个 near degenerate， 然后另外一个。
但是这个是不是就是说，如果 G prime 不等于 minus G 的话，它不会 degenerate， 就是说你如果要求 M1 要 degenerate，
对，但是为什么G等于 minus G prime？ 是说看这个 mass spectrum。
就是你如果是 G 等于就是我的 assumption 就是 semi-classical 你 argue 这个 strength 跟你一样，然后你 argue 这个 sign 你可以随便选，这样有2种方式，然后有一种的话是完全跟前不一样。对，当然我因为这个是还是一个比较 phenomenological 的 work， 所以我不能解释为什么这样取 minus 而不取 plus。
真的。
但是就是我如果取 minus，
怀疑就是它是
从那个一个
它是拉丁的时候就拿着出发，那你要产生那波分秒，
就是说这个 data
本来就是在它在考虑
almost degenerate，
我们没有看到自己取 minus。那可是按照他的说法的话，照理讲他的这些
其他不需要。
是飞来飞去。
这是说，
你的 laptop 是飞来飞去在地球翻飞。
不是他想分这些100出在哪个 model 上面。
对，那这样可是 monopole 它是在 compile。
input 只有那个 mass ratio。
对啊，那
我没有 addition，
可以看到一个，
我就是用实验的 mass ratio，
Neutrino，
就我加了一个 lambda， 然后有那个 addition， 就实验测到的 mass ratio input 进去决定那个 lambda。
那 monopole 是可以的
这样我
，monopole 它是一个 defect，所以它
不是啊，Neutrino 是 mass